So finally, we come to the last video of the methods block. And this is probably the most important one because it's going to kind of summarize everything we have talked about in these past 15 videos or so. And we're going to talk about all this from the perspective of two very important concepts. One is validity and the other one is reliability. So when we're thinking about a research study, or we're actually carrying out a research study, designing it, we should be able to think about the land of theory and the land of observation. So the land of theory is the one in which we make hypotheses, the one in which we try to think about possible connections between concepts, between constructs, and think whether one thing is causing an effect on the other thing. And it's essentially about what we think, how we think the real world behaves. And so when we're trying to establish a causal relationship between two constructs, then what we have is the construct that causes the effect, the construct that receives the effect, and then this relationship between the two of them. This is essentially what we think. This is how we think the real world behaves, or how the real world works. And then when we carry out a study, we go into the land of observation. So we start collecting data about this theory we have, about this hypothesis, and we carry out one study. So we collect the data and we talk about this one study we are carrying out. And so first thing we do is what we call operationalization. So we think about how we are going to measure the concepts of interest. We operationalize the cause construct, and then we come up with independent variables. This is essentially what we do. So for example, we apply a treatment or give a placebo, or we make a certain change in some independent variable like the temperature of the coffee machine, and then hopefully observe an effect in a dependent variable. A dependent variable, which again is operationalizing this effect construct. So we come up with variables that reflect this construct of interest, the concept of interest. And so this is essentially what we see. We collect the data about how this dependent variable is being affected. And then when we start analyzing the data, then we look for this relationship between the independent variable and the dependent variable. And this is what we test, which is again linking back to the construct cause effect. And so in the land of theory, we have our models, our theories, our hypotheses about how the world works, how one construct is causing an effect on another construct, and then we operationalize that into our research study. We have independent variables, dependent variables, we have a sample, we collect data, and then we test for specific relationships. And when we do this, we have to think about, well, the validity of our claims. Are we really measuring what we want to? If we establish a causal relationship between X and Y, we have to think whether that causal relationship is actually real or not, whether our claims are valid. And in doing so, we have to think about 4 kinds of validity, which can be represented kind of in a stairway, so that one is kind of building on top of the other. Let me start through the bottom. So the first thing we have to wonder about is, do we have conclusion validity? And essentially this means, is there really a relationship between the independent variable and the dependent variable? So are we sure that according to our data, we can establish that there is a relationship between the independent variable and the dependent variable? And we will see what are possible threats to this conclusion validity, in the sense that we might be saying there is a relationship when there's actually none, or the other way around. And if we are certain about it, we think we have conclusion validity and the relationship we are observing is actually real, then we can start wondering whether that relationship is really of a causal nature or not. So is the relationship really causal, or could there be third factors or hidden factors that are actually the cause of the effect and it's not really the independent variable that we think it is? So could it be because of something else? And this is what pertains to internal validity. So yes, we have a relationship. Now, is it really a causal one? Or is it maybe perhaps the other way around, or is it caused by something else? If we say we have internal validity and we are sure that we can establish this relationship as a causal one, Then what we have to think about is, all right, now do the variables that we measured really reflect the constructs or the concepts of interest? Because maybe they don't, or maybe they do to some extent, but not as much as we would like to. And so it might be the case that we can establish this causal relationship between the independent and the dependent variables. But really, when we think about it, we see that they are not really measuring the conceptual thing that we wanted them to measure, the concepts of interest. And if we can assume that, then we say we do have construct validity and we're really measuring the concepts we wanted to measure, then at some point we're going to have to ask the question of whether we can generalize these relationships, these causal relationships, to other populations. So we studied a certain sample, and we should in principle be able to generalize to the population that is representing that sample, but maybe we want to generalize to something else. So for example, we carry out a study in the Netherlands and we want to generalize our results back to France or Italy. Or we carry out our study in a certain field, we're talking about agriculture, and we want to generalize this to other fields. Or maybe we carry out our study with some kind of fruits and we want to generalize to other kinds of fruits. The question is, can we really do so? And we're going to see that there are certain situations in which we can't, or the extent to which we can. And if we can be sure that we meet all these 4 types of validity, then finally we can say that we have a valid claim. So whatever conclusion we draw from our study, we are sure that it's valid, that it's actually holding. And we could further more or less think that conclusion, internal validity, are of course in the land of observation, so they pertain to our observations. The construct validity is somehow linking between the land of theory and the land of observation, because it's the one telling us whether our operationalization of the concepts of interest is really good or not. And then the external validity has to do with the extent to which our theory really would hold or not. And then very much related to validity, we have reliability. And in this case, the question we're asking is, are we confident about our claims? So let's say that we do have a very good design, we have conclusion validity, we have internal validity, constant validity, external validity. The point is, how sure are you about your claims? If you are sure and then we see that they are valid, perfect. But maybe we have a very valid claim that actually is not so reliable. So generally speaking, how likely is it that if we draw a new sample and carry out the same study, we get to the same conclusions, to the same claims? And this very much relates to the random error. So remember that generally when we want to estimate a population mean, a population statistic, whatever that is, we have our estimate plus some degree of random error. And so the point is, what is the effect of this random error? Is it too large or not? And we have this random error because of sampling. Different samples are going to lead to slightly different results, but also just general variability in the measurement instruments. So imagine that you are measuring something about temperature, your sensor is likely going to have a certain degree of error. We have to talk about reliability there. And maybe some sensors have a very good reliability, but maybe some others do not. Or we are asking people to give us a rating or tell us what they think about, for instance, safety in their neighborhood. Well, we might find that depending on when we ask those people, we might have one result or another, or they just are not very consistent in giving the same answer when we ask them repeatedly. So the point of reliability is we don't have knowledge of the true values. We don't have knowledge of mu. That's the whole point. We're trying to figure them out. And so reliability cannot really be measured, cannot really be quantified. It cannot really be estimated. And there are certain ways in which we can estimate this reliability or this random error, right? We've seen, we could talk about confidence intervals, we could talk about standard errors. And in general, we could think about different classes of reliability or different types of reliability. For instance, we could talk about the inter-instrument reliability. So essentially, do different instruments give the same measurement? And by instrument, we mean actual mechanical instruments or people. If we ask someone to rate, I don't know, the quality of coffee, do we have the same results if we ask to a different person? So what is the reliability between those two? We could also think about test retest reliability, telling us exactly, does the instrument, the one instrument, give the same measurement over time? So if I ask you what's the quality of coffee now, and then you tell me something, and I give you the same thing tomorrow, are you going to be consistent in your assessment? And then we also have parallel forms of reliability. So it's more about the design. So if we have one sample from a population and we have a different sample from the same population, then we carry out our study, we get our results. Are they consistent across samples? So this is what reliability is about. And we're going to see by the end of the video how validity relates to reliability. But let's talk about possible threats to conclusion validity. So let's go through each of the 4 types of validity and see things that could go wrong. So conclusion validity mainly relates to the analysis, to the statistical analysis. What are things that could be threats to us having a valid claim? Well, for example, low statistical power or a high significance level. We've seen in the previous videos that it could be the case that we do not reject a null hypothesis and therefore claim that there is no effect, but it could be just that we don't have enough statistical power, that the effect is very small, or that we need a lot more data, and that's the only reason. So if we have these kind of claims that there's no effect based on a very small sample, then we are having a low statistical power and therefore our claims are not valid. Maybe unreasonable statistical assumptions. Maybe we run a test that makes a certain assumption, or somewhat strong assumption, that is really not met by our data. Then one could call into question the validity of our conclusion because we are breaking this assumption of statistical test. Maybe p-hacking or fishing for p-values, which essentially is trying to look into the data in all possible ways until we find a positive result. That's p-hacking or fishing for p-values. We know that there is spurious correlation and things just happen to be correlated. And we know that there's a certain probability of making a type 1 error, right? So maybe that's all it is. We are claiming something or some kind of relationship that turns out just to be a type 1 error. It's perfectly possible. Or maybe we have a poor control of third variables. We know that there might be a third variable mediating or moderating the relationship between two. And then if we do not properly account for it, we might miss some effect. Or think about Simpson's paradox. Those are things that could call into question the validity of our conclusions. And it's not only about the analysis, it's also about how we measure in general and how we carry out our study, the general settings of our study. Think about low reliability of instruments. If we have a, again, temperature sensor that reads basically whatever it wants, then maybe we find something, but there's no validity in here. Maybe noise caused by irrelevant events. So maybe we are carrying out a listening test, but there's a lot of traffic noise. Then those are things interfering with our study, and we have to properly take them into account. Maybe poor data management. Maybe we lost data. Maybe how we store the data is not reliable as it should be, and it turns out that there are modifications on the data that we don't know about. Maybe there's poor documentation. Maybe, and we find many times that we carry out a study, we get our tables of data, and then by the time we want to analyze, or years later we want to analyze our results, we don't really remember what this variable was and whether this was normalized or not, or whether this was accounting only for positive values, or what did the 0 really mean in this variable? Is it a missing number? Is it really a 0? What does that mean? So there's plenty of situations in which if we do not properly handle our data and document our data, we might claim things that are completely stupid. And just other general assumptions, like, for example, if we're asking people what they think about their boss, well, many people are not going to want to tell you what they think about their boss because they might fear being fired. So we might think that everything is perfect in our company, but it's actually not. It's just that people are afraid of saying otherwise. And therefore, we might have an invalid conclusion. Again, if there's one way to show this very well is through a comic. So here we have XKCD again, and the question was here whether jelly beans cause acne. And of course, scientists investigate this, and then they carry out a study, and they find no link between jelly beans and acne, with the p-value larger than 5%. So that's it, right? Well, someone said, I thought it's actually one color that causes that, right? And then, okay, study again. So now what they do is they carry out many different studies. So we have one in which we have purple jelly beans, brown, pink, blue, teal, black, whatever. And as we know, sure, one of those is going to be positive, right? Let's say in this case it was green. We know this could be just a type 1 error, and most likely it's just a type 1 error. Eventually, if you keep looking into the same thing, you're going to get lucky with your data and you're going to claim something. And so, of course, what's going to make the news? Green jelly beans cause acne. 95% confidence, whatever science says. This is completely relevant, and it's just a matter of properly accounting for all these threats to conclusion validity. And then there's one aspect of it that I want to stop just a little bit, which is pseudo-replication. So when we carry out the study, we can differentiate between experimental units and sampling units. So experimental unit is the one that receives a treatment. So let's say we want to study different surgical procedures, then the experimental unit would be the patient. If we want to try a new educational program, then the experimental unit would be the whole classroom. We apply a new program on a classroom, or maybe a set of classrooms, or maybe a whole school. And then we have the sampling unit, which is the one that corresponds to one observation. And in many different cases, we see that the two are not the same. So if we're looking into patients, both experimental unit and sampling unit are the same, because we apply the treatment on one patient and then we make an observation about the same patient. But in the case of the classroom, we apply the treatment on the whole classroom, but then we can make observations on each individual student. And the point is that, again, those two are not necessarily the same. If you want to think about it, any two experimental units should be able to receive two different treatments. If they can't, then they're probably sampling units. So in the case of the classroom, we might think about students. Can we apply a different educational program to two students in the same class? No, we can't. So that tells us that those are sampling units. We are measuring something, or we are making observations about those two students, but we are really applying the treatment on the whole classroom. And the problem is when we confuse one with the other, and we analyze the data at the observation level, thinking that that is where we are applying our treatment. And so the point with pseudo-replication is that it's going to inflate the sample size. And that is going to reduce the random error and increase the statistical power. But we know that this is completely superfluous. We are increasing statistical power when we shouldn't. We should average the sampling units within the experimental unit. So in the case of the educational program, for example, if we run it in a whole school and to each classroom we apply the treatment, we might have n equal, for example, I don't know, 6. We have 6 classrooms. So we really have 6 observations. Whereas students, maybe we have 300. Our sample size is not 300, it's 6, when we want to look into the effects of the educational program. And so this is one case, again, in which we would not have conclusion validity because we are inflating the sample size and therefore inflating the statistical power. Let's talk about internal validity. What threats do we have to internal validity? Well, first of all, confounding effects. If we have other variables that are correlated with the response and we do not properly account for them, or the design in our study is not such that it allows us to disentangle the effects of those independent variables, we might claim that there is an effect of something when in reality that effect is confounded with the effect of something else. And so we can't really say whether it's because of one variable or the other. We have no internal validity. We have selection bias, which is the case in which there are already differences between the groups. We just didn't know. So let's say that we want to see whether some medicine works or not. Then we give the medicine to one group of patients, and to the other group we give the placebo. If it turns out that those two groups are different in some sense, we might observe a positive response in one group or in the other that is not really caused by the medicine, but by that other characteristic of the sample. And if we do not know about it, then we don't have internal validity. We also could think about experimental bias, which is the case in which we are, with experimenters, unknowingly affecting the observations. So let's say that we try to have a new interface design in some software, and then we give it to users. There's one that we think it's a very good one, the new design, and one that we think it's not so good, the old design. Then, of course, if we are sitting next to the person trying the software and we point out all the, all the features of the new interface and always criticizing everything about the old interface, then we are biasing the subjects into thinking that the new interface is better. But it's only because we are sitting next to them, telling them everything about it, what's cool about it, and then we are influencing their response. There is also repeated testing, in which subjects kind of learn and remember between observations. So let's imagine that you run the same test, the math test, on students, and you always do the same test over and over and over again. Then by the end of the course, it's not that they learn anything, it's that they just remember the answers. There's also maturation and learning, where subjects just change during the study, and that affects the response. So it's not that whatever treatment we are applying actually has a positive effect, it's that they're just evolving in a natural way that leads to an increase in the response, for example, but it's not because of what we're doing, it's just how it was supposed to be in the first place. There's regression to the mean, where subjects are selected because of some characteristics in a pre-test. So let's say we have a class full of people, of students, and then we concentrate on the ones that have the lowest scores. We're going to get those, and we're going to teach them in a different way. We're going to apply a treatment, and then we're going to test again. And maybe we see that those students have an increased performance by the end of the course that the other students didn't. And we claim it is because, well, we applied this new treatment to them. We gave them this new program and they improved a lot more than the others. Well, actually, maybe it's just because in the time of the pretest, they were not doing so good, but if they were part of the regular program, maybe they would just get better as a natural evolution of a student that sometimes is good, sometimes is bad. That doesn't mean that our treatment has this positive effect. Maybe the effect was just expected to appear there just by its natural evolution. We have history threats. Maybe there are external factors or external events that are biasing our subjects. So think about, I don't know, I'm asking people whether they are happy or not listening to some music, but I'm going to ask that after September 11th. Then it doesn't matter what music you played, mostly they're going to tell you, no, they're not happy. And it's not because of the music, it's because all the historical context around us. There's diffusion effects, in which whatever effect we observe in one treatment is actually spreading across the other groups, for example, because there's interaction between the subjects in the groups. And there's a very, very, very long etc. When we talk about internal validity. There's plenty of other situations in which we cannot claim internal validity because there's some flaw in our study design. And one in which I want to stop a little bit is this one that tells us whether we are really, in a technical sense, carrying out an experiment or not. So we could have an observational study. This is not an experiment. There's no control of a treatment. Still, we could measure the response, we could measure independent variables, etc., but we do not have any notion of treatment or no control over the treatment. So let's say that we go to a hospital, we look into historical data about surgical procedures again, and we look into the data, but that's it, it's purely observational. We are not in control of any treatment or anything. If we go one step further, we could talk about quasi-experiments, in which we do have control over the treatment, so we decide which treatment to apply, but that assignment of subject to treatment is not random. So for example, we could decide on the treatment based on the age of the patient or the sex or the severity, as we saw in the kidney stones case, but that assignment is not random. And finally, we could have a true experiment in the technical sense. A true experiment is one in which this assignment of subjects to treatments is actually random. And by the way, not to confuse with random sampling of subjects, is once we have a subject or an entity upon which we can apply the treatment, the experimental unit, that assignment of treatment is random. So for instance, we get patients and we randomly assign the patients to treatments without looking into their characteristics, such as, again, age, sex, previous conditions, etc. Why is this important? Because the true experiment is going to give us the highest level of internal validity, the strongest internal validity. Why? Well, imagine that we are, again, in the case of patients, and imagine there is a factor that we don't know about that has a certain relationship with the response, but we don't know anything about it. So imagine that we, by coincidence, are assigning all the patients of a certain characteristic to one group, and then patients of another characteristic to another group. And that one characteristic is actually influencing the response. If we have no knowledge about it, we might be falling into the situation in which whatever difference we observe between those two groups is actually caused by these inherent characteristics of the patients that we don't know about, and we might be falling for that. But if we do a random assignment, then what we expect is that in both groups, we're going to be distributing patients from both characteristics all the same. So in this group, we're going to have both characteristics. In this other group, we're going to have both characteristics, so that they kind of cancel out when we compare between groups. So if there is such an inherent characteristics of the patients that is going to drive the response, it's going to affect equally this one group or this other group. And so they kind of, again, cancel out. So by the time we look at the data, this inherent effect is not seen as a bias, but rather as noise, because it's affecting both groups equally. When we talk about constant validity, we talk about the operationalization. So how we measure the concepts that we want to measure, what variables do we measure. And at this point, we have to think very, very carefully about how we're going to measure those concepts of interest. This is what determines validity. So usually there's no variable directly measuring the target concepts. Sometimes it's just not available to us for whatever reason. So we could think about developing several variables, using scales, indexes, etc. We have to make sure that whatever we measure really measures somehow the concept of interest, and that is not measuring something else that might be related to it. So in many areas, the measurement instruments are already developed. We have already, for example, Likert scales that are going to measure self-esteem or things like that. So we should first go through the literature and see if people tried to measure these concepts before us and how they did it, and just do the same, or maybe update that measurement instrument into something better. And it's particularly important if we're measuring something about people, because we are complex creatures. So we have to really think very hard about what we're measuring and how that relates to the concept we want to measure. Let me give you an example. So this figure is from a paper from a few years ago by some people from Princeton. And what they were claiming in the paper was that Facebook would have no users by 2021. Why did they say that? Well, what they were plotting here in the x-axis was time, and then here in the y-axis, how often would people search for Facebook on a search engine? And what they observed was this blue line over here. And then from previous data, they plot also MySpace over here in red. And it turns out that MySpace disappeared around here, 2012, and it was about the same time where people stopped looking for MySpace. And so what they were saying is, well, if we extrapolate this figure, then we'd say that by 2021, people won't be looking for Facebook on Google, and therefore it should be more or less when no users remain in Facebook. Now, as a happy coincidence, I'm recording this in 2021, and let me tell you, Facebook is not gone. And if you actually look into the data up to that time, 2014, the number of users in Google was just increasing nonstop. So if anything, Facebook was more healthy from the point of view of more and more users. So what went wrong here? Well, they were using this variable, how often people search for Facebook, as an indicator, as a proxy for something like the activity in the network. And of course, those are two very different things. And in fact, you could actually think the opposite. If people are looking for Facebook, it's because they don't know Facebook. So potentially that means there's even more users that would like to go and join Facebook. Or maybe there's just some controversy, as we found out recently, right? And so funny thing is the people from Facebook, they published another kind of a mockery paper. And what they were saying is, well, there's going to be no student in Princeton by 2021. Again, let me tell you, Princeton is doing very well, don't worry. So what they did was the following. They were plotting over here in this scatter plot, the search index. So again, how often people search for different universities. And then over here in the y-axis, the enrollment, how many students they had. And they found this correlation, positive correlation. We have here even some statistics about the strength of the correlation. And so what they were kind of seeing in this data was that the more often people look for a university online, then the more students that university has. And then they were looking at this search index for Princeton. And what they saw is that it was kind of declining over time. And so if they extrapolate this, they figured out that by 2021, no one will be looking for Princeton online. Therefore, Princeton will have no students, which is of course ridiculous, but that was the point. You can't just use the number of searches online as a way to measure something like the amount of students, the amount of users, activity, etc. So this is a very clear case in which the study did not have construct validity. And then finally, when we want to talk about external validity, we have to think back about this picture here in which we had some target population that we're interested in for our study, from which we draw a sample. So let's say we're interested in the whole country, whole set of citizens in the Netherlands, and we had a sample of 30 people. Now, in reality, the picture is not really like this. There's something more to it. So we have the target population, the sample. There's something in between, which is the accessible population or the sampling frame. And this is essentially a population from which we can actually sample, which is not necessarily the population that we are targeting. So those two things over here are not necessarily the same. Imagine, for example, that again, I'm interested in claiming something about the whole country, but I only have access to people in my region or in my city, or I only have access to adults, or I only have access to students. So there's an accessible population from which we can actually sample, but that might not be the same as the target population, and that might be even different from it. There might be certain differences between them that we have to think about, because anything that has to do with inferential statistics is down here. From the sample all the way up to the sampling frame, we have everything about the standard error, testing hypothesis, etc. So when we want to claim anything about the target population, we have to think more in qualitative terms. So external validity, how far can we generalize? Everything about statistics is going from sample to the sampling frame, and from there, how much we can claim is a matter of external validity. And so the point of external validity is, again, any of the factors involved in the process that we are studying poses a threat to external validity, because one could think maybe you don't have a representative sample, or your sampling frame is not really the same as your target population in terms of people, or in terms of treatments, or in terms of temperatures, coffee brands, machines, etc. And so if we encounter a case in which we do not have external validity, that kind of implies an interaction effect that we failed to observe because of our sample. So if we conclude there is a relationship between two variables in our sample and in our sampling frame, then if this relationship does not hold in our target population or the population we want to generalize for, it has to be because there's a certain interaction between this variable and another one that maybe reverses the relationship or just makes it larger or smaller. And so it's about a certain factor that is different between our population and the population we want to generalize to, and that's an interaction effect. And when we want to assess external validity, we do it basically from 2 points of view, either the sampling model or the proximity model. In the sampling model, what we say is that, well, we have a certain population and we draw a representative sample from it such that we do statistical inference and we generalize to this other population. And when we do this, we have to think that the target population, again, might not be clearly defined. Maybe by the time we carry out the study, we don't even know exactly what population we want to generalize to or we are interested in the first place. And it might be very difficult to draw a proper sample from it because, well, we don't know exactly what population that is. Maybe the sampling frame is biased. So imagine that I want to study something about music again, but I only have access to my music collection. And of course, that's going to be biased. Or I only have access to students, or I only have access to adults. Those are different from my target population. And again, representativeness is not guaranteed. We have one sample of data, and we know that if we repeat the sampling process, we are expected to represent the population, but given just one sample, maybe it doesn't. Maybe we just got unlucky. And then in the proximity model, what we do is establish the generalization to other populations that are close in some sense. So there are certain dimensions over which we could, in a more qualitative way, assess the proximity of the populations or how similar they are. And therefore, we could be able to generalize to those populations to the extent that they are similar across those dimensions. The problem here is that it's difficult because of unknown factors. Maybe we are not accounting for enough dimensions when we want to make those generalizations. Again, there's plenty of hidden factors and we just don't know about them. They are subject to kind of arbitrary degrees of similarity. So when is something sufficiently similar in terms of those dimensions such that we would be able to generalize? And then it's difficult to quantify anyway the certainty in that generalization. When we are in the sampling model, we know if it's a random sample from a population, we have the standard errors, and we have statistical models for that variation across samples. But in this proximity model, this is a lot harder because it's very difficult to quantify these differences. And so, in general, if we want to put everything together in one nice picture, which is going to be, by the way, the last slide of this blog, is this one here. We put together validity and reliability. So imagine that each of those points corresponds to the result from one study. So it's not just one single observation, it's one full study. And what we want to target is the bullseye, the center here of the target. And we have 4 possible options depending on validity and reliability. So we could have something like in the first example, in which we do not have a valid claim because on average, we are off the target. We have a certain bias, right? It's like on average, we are around here and that's not the center. And on top of that, we are not reliable because any given experiment is going to vary too much around that point. And so we are not going to be able to claim with confidence. It could also be the case that, well, we do not have a valid claim. It could be this one here. On average, we are around there, so it's far away from the bullseye, but we are reliable, meaning if we keep repeating our experiment, we're going to have a result that is very close to the others. And so all the results are kind of concentrated around there. That means we're going to be very, very, very confident about our claims. It just turns out that our claims are incorrect. We could have the case in which our claims are valid, but they are not reliable. So in this case here, on average, we are hitting the bullseye, but any given experiment could be arbitrarily far from it. So maybe in this case, we are very far from the truth. We are expected to find out the truth, but any one given study might be far from it. So we don't know. And this is what we would expect. And this is why we need to replicate. And then ideally, we would be in a case in which we are both reliable and valid, meaning on average, we have the result we want, we do measure what we want to measure, and any given replication of our study is going to be very close to it. So we have a lot of certainty. Now, again, this is what we want to have. Many times we're going to see that in the era now of big data, we have plenty and plenty of data around us, and we might be able to look into very reliable claims, but they're not valid because we're just using whatever data is available to us. But that's not necessarily the data we want to look at. If you want to think about it in another way, imagine that you're looking for your keys. You just dropped them and you don't know where they are. It's very dark and you're just looking around the street light because that's where you can see. But your keys are all the way over there, somewhere else that it's dark. You keep looking for them around the light. You're never going to find them because they are somewhere else. And many times that's what we do. We just look at the variables of the data that we have because, well, it's readily available to us, but we should be looking some other place. And what I want you to keep in mind at all times is that statistical analysis has to do with the spread of the points, not with their location. So all fancy statistical techniques we apply in our data, models and everything, they have to do one way or another with the spread of the points, with how far they are from each other. But they do not have anything to do with biases, with possible issues of validity. And so here I want to stress again that, especially in situations in which we are just given data and we're asked to analyze the data and to find what's in the data, find new insights, it's very important to keep in mind all the issues of validity, all the issues of design. How are we measuring? For what purpose? From where? All these issues that we've been talking about in these past 15 videos, they are kind of the basis for everything that comes afterwards in terms of analyzing data. It's not just we have data and we look into it and start making claims from it. Is we have to properly understand the data. We have to properly understand where it comes from and what it means so that we can make sensible claims from it. We can have a good analysis based on a proper understanding of the data we're looking at.